Morning, Bill.
Good morning.
Yeah, I just got on myself.
Okay.
How have you been?
Oh, fine. Yeah, the weather's been fairly stable here. Um, it's getting colder, but nothing to make life difficult yet.
We've had a couple of hot days the last couple, but today it's cooled off some. But it was like some the day yesterday, day before.
Yeah, but I hear a hurricane is headed in your direction.
Well, it probably won't get up this far.
No, I don't know. It won't be a hurricane probably by the time it gets to your area, but
Well, what I saw was crossing Florida. Who knows what it'll do? But interestingly, we've had a hurricane election. I don't know if you followed American.
yeah. Well, we don't get probably as much news as you do about it, but it's on a lot of people's mind as to what the next 2 years might be like.
They're expecting a tsunami, and they say for Republicans, but now they're saying it's going to be more like a ripple.
Yeah, not the Great Red Wave, wasn't that? That's what they called it, the Great Red Wave or something. But,
yeah, that's right. Great tsunami.
I have a friend actually in Palm Beach, Florida, and he's more or less in the path of the hurricane. But he said, "I'm not worried about the hurricane. I'm more interested in the election night celebrations, or well, not so much celebrations as just a form of entertainment." He had to interrupt our discussion yesterday because he said he had to make guacamole for all the people who were coming over to his place to watch the election results.
Yeah, they say that Trump's Mars-Largo, whatever it's called, Trump was rather subdued.
Yeah, he lives not far from that Mar-Lago, like I don't know, about 5 miles from the Mar-Lago estate. Right? But he said he knows all the time that Trump is in town because he sees all the black vans and like SUVs going up and down the street, and they have to take a different direction.
I see Jesus is on as well.
Good morning. Good morning. How are you?
Good morning.
That's good.
Have you been speaking about guacamole?
But about the American election.
Okay.
Yeah, the
Guacamole,
American.
of course, is
Yeah.
popular.
So I was saying that I have a friend in Florida who is not so interested in the election, but he likes the party, that they have when they watch the results.
Okay.
So he was making a very large batch of guacamole for the people who are coming to his place.
Oh, okay.
Big Mexican guacamole.
Yes.
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 Okay.
Okay, I guess we can start, right?
Yes. Dr. Sobczyk, you were going to talk, at least maybe in part, about triality, as opposed to duality.
Something like that. Let me, actually I'm very excited about what I'm going to present today, actually, and I hope I can transmit my excitement to you, or at least you can tell me where I'm wrong or not informed about. But anyway, I have very interesting things to say today.
Great.
So
Yeah,
I'll go ahead and share my screen, I suppose.
Yes, please.
Hope it'll work right. Okay, that's what I want.
Yes, that looks good.
Okay.
Okay, so what I want to talk about is, I've called it geometric algebras of complete digraphs. I was going to make a figure for it. Let's see if I can control this thing. Let's see, how do I change pages here? Okay, I guess let's see
If you
here.
click on the page at the side, you can, little image of the page.
Oh, yeah, I see it, exactly.
That'll
Okay,
work.
that's,
And
okay,
I
so,
think you can
so first of all,
also
let me
use
just
the
say
arrow
the
key.
diagram. Is everything all right?
Yes.
Okay. So what I first like to explain what I mean by a complete digraph. There's several different ways of looking at it. A complete graph of, say, n vertices is just where you're connecting all the vertices by by the combination of n things taken two at a time edges. That's pretty standard, is it not?
Yes.
So a complete graph is just a set of n vertices, and the edges are all the n. You pair off the edges, so it's a combination of n things taken two at a time. Now, by a complete digraph, well, it's a little bit less standard terminology that I'm using perhaps here. What I mean by a complete digraph is that you take a complete graph and you assign a direction, a positive or a negative direction to each of the edges. So I was going to make pictures, but I wasn't able to create them in a good way.
Okay, so you don't require that it be complete in the sense that it's bidirectional, right? So
No, I only have a single edge, but at the end have either, for example, if you have two vertices A and B, then you can go from A to B in one direction or from B to A. Okay.
Mm-hmm. Okay.
So a complete, well, for just two vertices, there's only one edge, but that edge can have either positive orientation from A to B, or what I'm calling a negative orientation when you go from B to A. That's clear, is it not?
Yes. Although exactly what you define positive or negative might be arbitrary.
Well, I just mean, I'm calling positive when you go from A to B and negative when you go from B to A. So if you have two vertices named by A and B, then you go from A to B for positive, B to A for negative.
So if you had some global way of assigning an order to the vertices, then you could unambiguously say what is positive and what is negative. But
yeah, that's true. Yeah. Well, I'm using alphabetically, of course, A to B, B to A. It's the same thing, really.
Sure.
Okay, I might just change that later on, but I've been pretty trying to get this done in time. So, okay, so let's go ahead and read the abstract. A complete digraph is a complete graph in which every pair of vertices is connected by a directed edge. By a geometric algebra, I mean a Clifford geometric algebra, of course. A null vector V, okay, this is you're already familiar with. A null vector V is an algebraic quantity such that V squared is equal to 0, okay? And then I denote what I call the universal algebra generated by taking all sums and products of these null vectors over the real or complex numbers. And I call that the algebra N. And I give a reference, which I have. I'll send you a copy of this at the end of the session. I haven't had time to really, I was working on it right up to the end. Okay, so again, the rules of addition and multiplication in N are taken to be the familiar rules of addition and multiplication of real and complex square matrices. Well, that's just a simple way of defining what the rules in this algebra that I'm assigning to N. Finally, I define a pair of null vectors positively or negatively or correlated if their inner product is plus or minus 1/2, respectively. Remember, when I said everything is equal, positively correlated, that means that AB plus BA is equal to 2A dot B, okay? So A dot B for those nilpotents then is 1/2. Negative correlation, it's minus 1/2. The main result of this paper or this work is that each complete digraph of N vertices represented by N equal to P plus Q correlated null vectors defines a geometric algebra, some geometric algebra GPQ, okay? Well, I'm not going to be able to prove all that, but I think that it's true. And I'm only going to go in this talk to consider the cases of 1, 2, 3, and 4 vertices, which we label with the nilpotents A, B, C, and D, okay? Okay, so that's what I'm explaining here in the introduction.
One quick question.
Uh-huh.
So you associate a vector with an edge of the digraph or with a vertex?
Okay, the edge, well, it's a complete graph, first of all. So the edge, of course, is if you have 4 vertices, then there are a total of 4 things. You take pairs of vertices, connect them all together with an edge. So that means that there are 4 things taken 2 at a time, or 6 edges for a complete graph, okay? So I'm only going to consider graphs up to complete graphs with up to 4 edges, okay? And I'm going to show you how to associate each of those graphs with a geometric algebra. In other words, I'm not defining geometric algebras now in terms of matrices or their component matrices of coordinate matrices. I want to define a geometric algebra completely in terms of these nilpotents, which represent the vertices of our complete graph.
I see. Okay, so so we should sort of label the vertices with a null vector, right?
That's right. So if you only have 2 vertices, then of course you have a directed line from A, which you label by A, and the second point will label by B, the vertex. Okay, for 3 vertices, A, B, and C, then you can have the edges A to B, B to C, and C to A again, okay? That's the complete graph. In that case, it's very simple because 3 things taken 2 at a time is exactly 3, right? 2 times 1 divided, 3 times 2 divided by 2 is 3, okay?
Okay, but you haven't
So
said to
again,
us,
I'm
told us
talking
how, you've said what the vertices represent, but not what the edges represent.
Well, the edges, all I'm saying is that there are edges, and I'm labeling the direction of those edges by the inner product of the null vectors, which represent the vertices. Okay, so I'm gonna show that. Okay, so let's look at the simplest case, a pair of null vectors. So what we're talking about here then, the corresponding digraph is a line segment from A to B, where A squared is equal to 0 and B squared is equal to 0. And I'm going to consider the case where AB plus BA is equal to 1. Okay, that means that the inner product between those two null vectors is 1/2 from what we've talked about before. Is that okay?
Yep, sure.
Okay, so that one, we say the null vectors A and B are positively correlated if, I've changed it, I used to say correlate, I used to say compatible, but now I'm using the word correlated. Okay, so two null vectors in N are general algebra generated by all nilpotents, null vectors rather. Then if we just take a pair of them, A and B, then we say that those null vectors are positively correlated if the inner product of those null vectors is equal to 1/2. Okay, or that's the same thing as saying AB plus BA is equal to 1. Or that says that A dot B is equal to 1/2. And they're said to be negatively correlated. In other words, we're going to let the edges now from B to A if A dot is equal to -1/2. Okay?
Excuse me, I have many many questions here. Maybe I don't understand the idea, but I think that you are substituting the arrow by the dot.
That's right. Well, that's right. The dot product between the vectors, null vectors, defines the direction, the directed line segment from A to B. Okay?
Yes, the directed line, because you are thinking in directed graphics.
Exactly.
Directed graphs, and
Exactly.
then
I'm saying a digraph is where you have a complete graph. Complete graph is just all the vertices are connected by one.
Yes, all are correlated.
Exactly.
All the vertices are correlated.
Exactly.
Yes, but the presence of one correlation in the graph is understood, for example, like the value in your table 1.
Well, that's right. AB plus BA is equal to 1 in the case they're positively correlated. Okay, well, that's the dot product in geometric algebra. A dot B is equal to AB plus BA.
And we can think that A have not identity because the correlation is 0.
Well, that's right. A times A is equal to 0 because it's a nilpotent, a null.
Yes.
A null.
Okay, but then we have not identity in this in these relations.
Well, I'm defining the dot product between the null vectors A and B to be equal to 1/2. Okay, it's just, I can do that. We have two null vectors, and I'm saying let those null vectors have an inner product, A dot B equal to 1/2. In which case we say that the directed line segment is positively oriented. Okay, the first vertex is labeled by the null vector A. The second vertex is labeled by the null vector B. Now, I'm sorry I don't have a picture, but I just wasn't able to draw these pictures.
I think what Jesus is saying is that you have the requirement that in your digraph there are no loops of length 1.
Well, that's
Okay.
right. That's what we're talking about, a complete graph. A complete graph only has n pairs of, n things taken 2 at a time.
Yes, but it has,
Edges.
it may have loops, but it
No,
cannot have
I
loops.
don't want it. No, if you have n vertices, what I mean by a complete graph is exactly one edge for every distinct pair of.
Yes, that's the point. That they have to be distinct pairs.
Okay, okay. Yeah, thanks. Yeah.
Yeah, so it would be nice if I had made pictures, but I had a lot of trouble with pictures, or anyway. But again, so we're only thinking about a directed line segment in the case of two vertices, and a triangle in the case of 3 vertices, and with 4 vertices, there are 6 edges in a complete graph consisting of 4. Okay, all the vertices are paired together, so that means that all the dots. So we have 4 nilpotent, or 4 null vectors, A, B, C, and D. You can think about going clockwise around the okay, and then all the inner products of those 4 null vectors, which name the vertices, the vertexes. You think about it as a square, A, B, C, and D going around clockwise.
But there might be some confusion here that you've used dot for multiplication.
Well, that's Clifford algebra now. That's geometric algebra.
Table one.
Yeah, that's right. That's the multiplication table.
You've labeled that dot, right?
Well, that's true. I could have left it open because, that's right. I could just leave it as blank. Maybe I should get rid of the dot there, right?
Because you're not talking about inner product here.
No, not there. The multiplication table is just the geometric product. So I should leave that blank, I guess. It's adjacency, but I put dot in there. Maybe I should. Yeah,
Okay.
That's confusing.
Is the adjacency matrix? The adjacency.
Yeah, that's the same table that I gave you for the matrices. So you can see how I'm getting my geometric algebra, which I associate with a directed line segment. It's just the geometric algebra G11 with 1. Now you look at A plus B, if you square that, you'll get +1. If you look at A minus B and square that, you'll get -1. Okay, I think I do that here. Okay. So let's just go on. You'll see it a little later. So this is the multiplication for 2 null vectors, which are positively correlated. That means they satisfy. Okay, so that's not a dot here anymore. That's just here, there, it's gone. Okay, I don't want that dot. It's just adjacent.
Star or something.
Well, nothing, just nothing there, because we're just multiplying. Okay, I'm sorry about that dot there. It's confusing. But anyway, so here it is, AB plus BA. That's according to this table. We're using the multiplication in this table. And you can see that AB plus BA is equal to 1. Well, that's exactly what we have here. So that's the geometric product that it's defining now in terms of those null vectors. Okay. Okay, but now the new idea is that we're going to also consider when the dot product is defined to equal to -1/2. And that's what we're associating with the directed line segment going from B to A rather than from A to B. So if A to B is a positive direction, then B to A is a negative direction. And that's the second multiplication table. So that's this case where AB plus BA is equal to -1. There you have it. A times B is AB, but A times BAB, well, if you multiply this equation on the right by B, then you see we get AB squared. Well, you can see A times, let's see, do I have this right? Yeah, A times AB is 0. So, okay, well, you can see if you multiply this identity on the right up here by B, then you get -B here, and you get AB squared is equal to 0. AB squared is 0 here. You see that, okay? But in this case, Can you still hear me?
Mm-hmm. Yes.
Okay, I was afraid I might have dropped out there. So that's the case when they're negatively correlated. The edges are negatively correlated, or you're reversing the direction of all the arrows. So you're going A, B, C, and D is one, but now you're going from, well, you're connecting all the vertices with the opposite direction. Okay, so we can go on here. If the null vectors A and B are positively correlated, then the null vectors minus A and B will be negatively correlated. Okay, well, I'm not going to say much about that, but you can check that out. You just replace A by minus A and leave everything else the same. And this first table becomes the second table for the null the null vectors minus A and B will be negatively correlated. That's all I'm saying here. Okay. Okay, so here we have the geometric algebra generated by the positively correlated null vectors A and B is G11 equal to RAB. So we're extending our real number system by two nilpotents, two null vectors, okay? Two null vectors, A and B, okay? So when you extend the real number systems to include two null vectors, which we call A and B, which have square 0, and if we define E equal to B plus A and F equal to B minus A, then we'll get, then you'll see the, well, that's what I'm doing here. That generates the geometric algebra G11, where the E and F are orthogonal. You can check it. If you multiply B times B plus A times B minus A, you'll get E times F is equal to, well, E squared is equal to 1, and F squared is equal to minus 1, because remember, BA plus AB is equal to 1, and BA times minus BA is equal to minus 1. Okay, you remember that from before when I was talking about these things. Okay, so in other words, the geometric algebra G11 and the standard basis for geometric algebra, or Clifford algebra, is G11, which is the real numbers extended by a vector which has square plus 1, which we call E, defined in terms of the null vectors by B plus A, and B minus A for F. Okay, and so that's the geometric algebra G11. Okay, if instead the null vectors A and B are negatively correlated, satisfying this table 2, then in this case, the vector E defined by B minus A will have positive square, whereas F will have negative square in that case. So we're actually defining the geometric algebra G11 in terms of two nilpotents A and B in a different way in this case, but they're the same geometric algebra. So in other words, let's see. Okay, the complete two digraphs associated with the positively or negatively correlated null vectors A and B and N are directed line segments with vertices A to B and B to A respectively. They both are associated with the geometric algebra G11. Okay, is that clear?
Yes,
The idea is clear, but I have some question here, because in fact, in the lower arrow here, you have again the product A dot B equal 1/2. And I can see that in the table.
That's right here. A dot B is equal to 1/2, or positively correlated. But if you say that AB plus BA is equal to -1 instead, then you're saying that the inner product is -1/2.
Okay, I understand that. But in the table, in terms of correlation between the nodes, I can find that 1/2.
You mean for E and F?
Yes, for example, here, okay, I understand this table like an adjacence table. Then we can imagine here like arrows that are with in terms of all the elements of the graph. In fact, I need for this one node called A, one node called B, one node called AB, and one node called BA.
No, I'm not putting AB and BA in the graph. I'm just using the graph is labeled by the null vectors A and B.
Yes, yes, but then what is the meaning of this table? Because then, okay, A is not adjacent with itself. Yeah, okay, and then is adjacent with B because exists AB, and B have adjacence with A and not auto-adjacence. And then the graph here is have all this information in the first part of this table.
Yeah, you could extend, of course, but I really only want to. What I'm talking about here is I'm trying to characterize complete digraphs by make a characterization in terms of the geometric algebras, which can be defined by what I'm giving you right now. Okay, so a digraph of order 2 is just A and B. Now, if it's directed, so it's A to B. It's a directed arrow, or the other orientation is B to A, which is the -1. Now,
then
what I'm doing is I'm trying to reduce graph theory to geometric algebra, to be able to calculate things about graphs, complete graphs at least, or digraphs, what I'm talking about now, in terms of properties of the associated geometric algebra.
For example, if we have one graph with 4 nodes, for example, one square.
Well, I'm going to do that one in a minute. We'll talk about that. But right now, the simplest case, of course, is just two null vectors, A and B.
Two nodes of this graph with 4 nodes, for example. No?
Okay, well, let's go systematically. First of all, we just consider 2 null vectors, A and B. Now, I'm using those null vectors to name the vertices of a directed line segment, A and B. I'm not saying where that line segment is. I'm just saying that's our line segment. And now we say the line segment is positively oriented if you go from A to B, and that's when A dot B is assigned 1/2, the dot product, 1/2. And if it's going the other way, B to A, then it's -1/2. That's the direction of the edges, or the direction of the line segment then has 2 possible directions. So given a line segment, you can orient one side going one direction as plus, and the other going the other direction as minus. That's all. Okay, well, let's go to the next case. Maybe it'll become clearer as we go along. Okay. So the next case, okay, anyway, so the conclusion of that discussion is a complete digraphs, the language I'm using, complete two digraphs associated with the positively or negatively correlated null vectors A and B and N are the directed line segments with vertices A to B and B to A respectively. They are both associated with the geometric algebra G11. And that's all I want to say about that. Now let's look at the case for three null vectors. So three null vectors A, B, and C and N are said to be completely positively correlated if A dot B equals B dot C equal to C dot A is equal to 1/2. Well, of course, we can write that in geometric algebra as AB plus BA is equal to 1, BC plus CB is equal to 1, CA plus AC.
Oh, I lost.
Yes.
Yes, we lost the connection.
It's interrupted here.
Interrupted. Yes.
Perhaps he will reconnect.
Yes, we can wait for a while.
Okay. Oh, here we go.
I dropped out there for a minute.
We lost
Yes,
you for a few minutes.
No, okay, I could turn on my Mexican cell phone. It works. It's better. It's AT&T. Anyway, am I all right now? Maybe I can go back to my share screen. Let's see if it works. Okay.
Okay.
Is everything all right? Or am I dropping out?
Yes, that's
Now.
good.
Okay. So let's talk about three correlated null vectors now. So three null vectors A, B, and C are said to be completely positively correlated if the inner product of those null vectors, which represent vertices, A dot B, B dot C, C dot A is equal to 1/2. Negatively correlated if it's equal to -1/2. Okay, so those define the edges then. Okay, and now let's go on. A set of correlated null vectors is said to be of mixed correlation if they are not completely positively or completely negatively correlated. Okay. Okay, so let's suppose that the three vectors A, B, and C are positively correlated, satisfying A dot B equal to B dot C equal to C dot A equal to 1/2. And we define, just as before, we define E1 equal to B plus A, F1 equal to B minus A. Well, so we know those define orthogonal vectors, which are anti-commutative. Okay, that's what E1 squared is equal to 1 is equal to minus F1 squared, okay? And now we have A wedge B is equal to 1/2 B plus A wedge B minus A. Well, that's the same thing as E1 times F1. Well, that's a bivector, okay? But now we're going to get another vector here. What we do is we define F2 equal to 4 A wedge B dot A wedge B wedge C. Okay, well, that's just the usual. We're taking, it's by definition in Clifford geometric algebra, we do that by taking, so 4 of this is equal to 4. We take the dot product of B with A wedge B wedge C, and then we dot it with A. And that's essentially Gram-Schmidt orthogonalization. Okay, so we're orthogonalizing the trivector defined by the outer product of the null vectors A wedge, B wedge, C, okay? So there's where we could use the bivector A wedge, B wedge, C to define the area. Well, I'm not going to talk about that, but you can see, we can say many more things now when we express everything in terms of geometric algebra. Okay, so the new vector F2 is equal to this. Well, okay, if you do that calculation, I'm sure you're not so familiar with these calculations, but it just comes down to C minus A minus B. That's what defines a third. Well, okay, now if I calculate, if I take C minus A minus B and I square that, that's the same thing as taking C minus A minus B dot C minus A minus B. And you can check that that's equal to -1, okay? So in other words, and if you look at F1 dot E1, using just those rules in the multiplication table I gave you, that you'll find that F1 dot E1 is equal to F1 dot F2 is equal to 0. So that means that E1, F1, and F2 are orthogonal. Well, that's what defines the geometric algebra G12, okay? So that's equal to the real number system extended by E1, F1, and F2, but that's really the same thing as the geometric algebra that you get when you extend the real number systems by three null vectors, A, B, and C, which have square 0, which name the vertices of a complete digraph of order 3. Okay, well, I'm not going to, now we can take the other case. Suppose that A, B, and C are negatively correlated in this case, satisfying 4. Well, remember what 4 was. That just says we're associating the edges of the triangle, which is by the edges, A dot B is equal to minus. So reversing the direction and going around the triangle, instead of going around clockwise, A, B, C, we go counterclockwise, C, B, A. All the line segments on that triangle are directed in the opposite direction. And then doing that, we define E1 equal to minus B, F1 is equal to A plus B, that's the negative for 2 vectors. And then we define E2 equal to A plus B minus C. Well, essentially, that's the same as this one. It's not much at all there. It follows that G21 is associated with the graph, the digraph, which is the Clifford algebra, the real number system extended by 3 null vectors which have square 0, whose inner product is equal to -1/2. Okay, so that's the 2 simplest cases, and I hope you can it's really pretty simple ideas. The way things work out. I'm completely surprised by this. At first I only wanted to say that AB plus BA is equal to 1 is duality. Well, I think that duality that people usually use is just extremely confusing because, well, it just misses. I think that's why this stuff hasn't been done before. I don't think it's been done. Maybe it's already been done. I know at this CGA conference that I attended, there were people that were using geometric algebra for graph theory, but I don't think they did it in this way, if I remember correctly. So anyway, this is.
I saw here. I think that I can understand your idea, because if we have 2 nodes, we can associate this graph with a category. And then if we have the morphisms for the A node to the B node, then we can build the opposite category going from B node to the A node. And then you are presenting this like a sequence of actions that finally give to you the, I don't know if I can say identity, but one, you get one because you take AB and after you take BA and you add both and then you get one. No? And this is the same that arriving to the start point. Then I think I think that it is too much interesting your presentation, Professor. Mm-hmm.
Well, like I say, I'm limited by knowledge of category theory. So maybe that's what's made it possible for me to look at things in this way, because I just don't have that language of category theory at my disposal. Well, some of it, universal algebra and so on. But anyway, I think this geometric algebra, I don't need the category theory. All I need is this N of the algebra, universal algebra generated by null vectors, which have square zero. That's all you need. If you start with the real number system and you take all these null vectors, A, B, C, and there's infinitely many of them that you can invent, then you're completely characterizing geometric algebras in terms of complete digraphs, which I think is pretty interesting.
But you need complete diagrams for this because your formulation is independent of that.
No, I don't think it is, but this is just the way I started thinking about it. But that's right. I believe that you can do the same thing for much more general graphs. And yes. I have some ideas about that, but I can't do that. There's too much to do. In fact, I'd like to do the calculus of this stuff too. I think that would be I can see how to do calculus. People usually, that's the thing, Minkowski space-time. Well, people study Minkowski space-time using the Dirac matrices. Well, okay, they're the corresponding geometric algebra is G13. The gamma vectors, gamma 0 squared equal to 1, gamma 1 squared equal to gamma 2 squared, gamma 3 squared equal to -1. Okay, but now we're associating. We're going to find the digraph that corresponds to the Dirac algebra or space-time algebra. That's the space-time algebra, the Minkowski space-time. Okay, but let's look at the simplest mixed completely correlated cases for 3 null vectors. So that's the case where I have 2 of them. So we have 3 vertices, A, B, and C, where A dot B, the edge connecting A and B from A to B, is positively 1/2. B dot C is positively correlated, but C to A is negatively correlated because I say it's equal to minus C dot A. So C dot A is equal to -1/2. So that's the mixed case. When I'm calling the mixed correlated cases for 3 null vectors.
But why do you need C here for association?
Well, we need 3 vertexes for a triangle. You have 3 vertices, A, B, and C.
But in your table, you use A and B only for defined operations. But I think that you have any number of nodes, any. And then
no, that's right. That's right. So what I'm doing, really, I'm inductively constructing these things, okay? So we can construct N3, 2, 1 by taking what we did. Well, there's several ways of doing that, but you can see we can use what we did for the earlier cases, like 2, 1. We can take E1 and E2 that and use that to help us find the corresponding geometric algebra for N2, 1, where in this case, we're defining the edges to have these orientations. A, B have the orientation 1/2, B dot C has and minus C dot A is equal to this, okay? Okay, well, I don't really carry out the analysis here, but what we'll do is you can define E1 equal to B plus A, F1 is equal to B minus A, and E2 is equal to B plus C minus A. And that gives us a geometric algebra G12. Okay, it's 2. That's the interesting thing, this E2 defined by B plus C minus A, that's different than what we did over here with C minus A minus B. So that's now different than, well, yeah, well, maybe it is the same again, right? Let's see. No, C, A plus B minus C. Well, it's the same again, okay? So that's right. So we're associating two geometric algebras with this particular graph. Well, that's because, well, okay. That's all I can say about that right now. Okay, this completes the study of 3 completely correlated null vectors. The complete 3 digraphs associated with each of the completely correlated null vectors at the 3 vertices A, B, and C of the complete digraph are listed below, together with their associated geometric algebras. Okay, so here we're associating with N330, the geometric algebra G12. Okay, and I'm using this notation. So A to B to C, positive, 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 okay? It's just a way of writing that, trying to visualize that. So that's, say, going around our triangle in the positive direction, clockwise. Okay, 303, that's when we're, the N3 of 3 null vectors corresponds to the geometric algebra G12. And that, instead of going A, B, C, we go counterclockwise. A, B to A, C goes to B, goes to A, okay, the other direction, counterclockwise. Okay, so that's, so the correlated 3 null vectors correspond to the geometric algebra positively correlated G12, negatively correlated G21. The mixed correlated 2,1 corresponds to G21, the same as this one. And one, so we're associating really 2 geometric algebras with the particular graph, okay, whichever is more convenient. So really it's not a one-to-one mapping of okay, well, okay, the 4 case, because I think you're getting the idea. So maybe we'll go on to I introduce a little more terminology to clarify these ideas, okay? So we can start. Okay, section 4, geometric algebras of complete 4 digraphs, okay? A complete graph with n vertices has n things taken, combination of n things taken 2 at a time, which is of course equal to n times n minus 1 over 2 edges, okay? If we allow each of those edges to have 2 orientations, positive and negative, and name each of the vertices with the completely correlated null vectors, A, B, C up to n, there will be a total of n things taken two at a time plus one completely correlated digraphs n, j, k, and that's of course a subalgebra generated by these n null vectors. And okay, and I guess you can say we could say that they're correlated, completely correlated, if A wedge B, A1 wedge A2 up to A wedge AN is not equal to 0. That's really where the Grassmann algebra comes in. Oh, okay, maybe some of this stuff has already been done in terms of Grassmann algebras. In fact, maybe in this conference, the CGA, AGA, CGA conference that I told you about, maybe there was a guy that used Grassmann algebras to do graph theory. I listened to his talk, but I didn't remember all the details of it. Okay, so the case considered here for n equal to 4, there are 4 things taken two at a time plus 1, 7 completely correlated digraphs of the form n4 jk, where j plus k case is equal to 4. I should put that in there, I suppose. The sum of those two numbers must always be, it equals the number of edges. J plus k is equal to the number of edges, okay? Which is 7, okay? You can see that. 4 things taken two at a time plus 1 equals 7 correlated digraphs for JK. Okay, so here they are. We denote the different digraphs by N4JK, 6, 0, 5, 1, 4, 2, 3, 3, 2, 4, 1, 5, and 0, 6. 1, 2, 3, 4, 5, 6, 7. Okay, that's where I'm getting this formula here. That's the number of directed edges of a square with, you can think about the square as A, B, C, and D. We go A, B, C, and D with positive orientation. Well, all the vertices are oriented positive. Of course, it has the diagonals. So remember, the size of the square determine 4 edges, but then you have the diagonals, and they're assigned a positive and negative orientation as well. So where each JK gives the number of edges of J positive and K negative orientations, respectively, of the 6 edges of the square. Okay, can you hear me still?
Yes, yes.
Yeah, that's good.
It was.
Okay, that's good. Okay, well, so let's do the first case. I haven't done all these cases because it's just a little tedious, okay? So case 4, where we have all the edges are oriented positively, okay? So I call that N4 of plus, 6 pluses, 2, 4, 6, okay? For A, B, C, and D, which are the vertices of the graph of a square, A, B, C, and D. Referring back to 3, we define E1 equal to B plus A. See, now I'm using, it's kind of an inductive type thing that we're doing here. Otherwise, the calculations be, that's what we're trying to get a general inductive argument. I haven't done it all yet, though. E1 is equal to B plus A. F1 is equal to B minus A. F2 is equal to C minus A minus B. Okay, as in the case N30. We've already done that case, so I'm just picking up these definitions from the case N30. And now note that E1, F1, F2, okay, that's the same thing. If you expand this product, the wedge product, A plus B minus B minus A plus C minus A minus B, you'll find that that's equal to 2 wedge A, wedge B, wedge C. Or maybe it's, I guess that's right. Maybe it's more, maybe that number's wrong there. I'm not sure. Let's see, we're going to have B wedge. No, I guess it's all right. Okay. Well, anyway, I think it's right but anyway, let's go on. Okay, I guess it is right. I think it is right. So naturally, we then define the new number. This is the idea. We take A wedge B wedge C and we dot it into A wedge B wedge C wedge D. Okay, so again, that means we're decreasing, we're taking the contraction, if you want to look at it in terms of differential forms, or it's a contraction. It's three contractions of A wedge B wedge C wedge D. Okay, so that's the same thing as the bivector A wedge B dot the first contraction, C dot A wedge B wedge C wedge D. Well, if you calculate that out, you get this. You get 4 times, and now we've dotted out the C. Note that when I take C dot C, I get that equal to 0 because C is a null vector. Okay, so the inner product of null vectors is 0. Okay, so what we do is we get B wedge C wedge D because I'm C dot A gives me 1/2. That's why I'm reducing this to 4 now. And then we have B wedge C wedge D. That's this bivector. Then we take minus, change the sign, dot C dot B. Well, that's 1/2 again. So again, we're getting a 1/2. But now we take this one out. We have minus A wedge C wedge D. Minus A wedge C wedge D. Now finally, we dot C with C, we get 0. So we leave that one out. And then we have C dot D is 1/2 again. So again, we get this trivector dotted with B then, okay? Okay, now if we take B dot in this expression, you get, again, B dot B is 0 because it's null, and then we have B dot C. Okay, anyway, you get this, and that's the same thing as A plus B plus C minus 2D, okay? Now, if you square this element G, which is a vector, we'll find that that vector square is equal to -3. It's for this reason that we define F3 equal to 1 over the square root of 3G, which is the quantity 1 over the square root of 3A plus B plus minus D. So that means that F3 squared will be equal to -1 then, because G squared is equal to -3 then. Again, you have to calculate this. You know, it becomes a little tedious and you can't do that much. I haven't done enough of them really, but taken together, we have shown that G13, you see, that's the Dirac algebra. G13 or space-time algebra is equal to N4 of 6 edges positively correlated, and that's a subset of this universal algebra, which I call N. Well, okay, but we also know from previous talks how we can get a matrix, you know, a coordinate matrix of that geometric algebra and so on. But actually, this is quite different because we're defining geometric algebras in terms of graph theory, really. In fact, digraphs, complete digraphs. Okay, so here it is. So G13, the geometric algebra G13 consists, standard basis is 4 orthonormal vectors, E1 squared equal to 1, F1 squared equal to F2 squared equal to F3 squared equal to -1. And that's the same thing as a Dirac algebra. The real number system extended by 4 nilpones, positively correlated nilpones, which we can think of as naming the vertices of a square, a directed diagram of a square. Okay, and the only other case I'm going to talk about. Okay.
Excuse me, Professor. One question here. Can you repeat what do you understand like the value of this signature that you are putting here inside of N4.
Uh-huh. Okay. Yeah. Well, you can see, well, I say it's 1, 3 because we used the earlier cases to define this case E1, F1, and F2. And here all I've had to calculate is my F3. We found another orthonormal vector, which is orthonormal to E1, F1, and F2, okay? So this is an orthonormal basis of 4 vectors with signature E1 squared is equal to 1, F1 squared equal to -1, F2 squared equal to -1, F3 squared. Well, that's of course just the Dirac algebra. Dirac algebra uses matrices. Gamma with 0 squared equal to 1, gamma 1 squared equal to -1, gamma 2 squared -1, gamma 3 squared -1. So you see how the space-time algebra arises then in terms of the geometric. But I'm not using gamma matrices.
But we are starting from one complete graph.
A digraph. Each edge is
diagram.
oriented positive or negative.
Yes, and then you are only taking some different kinds of travels that you are making in the graph. Is that okay?
Yes, exactly. In fact, that's why I think these ideas can be generalized, but I'm restricting it because I'm trying to understand in, the case of where you take a square and you just assign an orientation to each of the edges, all the different possible orientations of the edges.
Yes, because in your graph, we can make many different kinds of travels.
Well, that's right. We can have double edges and all the rest of the stuff too. But I haven't investigated that. I haven't thought about that.
Okay, you select one special travel in that graph that have this kind of signature.
Yeah, that's right. That's because I'm associating each edge with a given positive or negative, which I can assign any way I want, really.
Okay.
It doesn't, I can take the 4 edges of the square, A, B, C, and D. Okay, you can say A, B is positive or negative. Choose whatever orientation you want. Okay. But I'm only, so but it doesn't matter which ones. It could be positive, negative, positive, negative, negative. I'm identifying those cases with the same. Okay, so that's why I'm saying, I can be it's a little confusing. I know it is, but because people, again, speak about complete digraphs, there's different definitions that I've looked at. I haven't many. I'm not really all that, I'm no expert at graph theory, but I think that this seems to be, now I remember more clearly, there was a guy that used Grossman algebra to label the vertices. Well, of course, that's exactly what I'm doing here, the vertices of the graph, but I'm assigning the edges. That's where I get the geometric algebra. And I guess that's the really thing that's only new here. But I also think it's important in quantum mechanics because notice that the interesting thing is that I'm assigning an edge to plus or minus 1/2. Well, of course, 1/2 is the spin of an electron and, positive spins, negative spins of 1/2, all multiples of 1/2. So that's exactly that's why I think this is probably extremely important language for quantum mechanics as well, associated with graphs, complete digraphs, okay? But I'm calling complete digraphs.
Yeah.
Okay, well, let's look at one more case here. That's all I really have worked out. Well, I've done 2 cases more. I've done the cases where all the edges are associated with a negative orientation, which simply means that the dot products of any 2 vertices are negative, okay? Okay, now going back to 4. Okay, that 4 is a negative correlation. They're all negatively correlated, null vectors. We now define, again, as before, E1, E2 equal to A minus B, F1 is equal to A plus B, and E2 is now equal to C minus A minus B, as in the case N3, 0. And we note that E1, F1, E2, the 2A wedge B wedge C. Okay, similarly, we find that, okay, now I'm defining G again as the contraction of the 4 vector A wedge B wedge C wedge D by A wedge B wedge C. Okay, and I calculate that out. Again, it's just dotting this stuff. You might look at one step here. Okay, so this is the same thing as 8, and I contract with C. Okay, well, in this case, I first contract C dot A is minus 1/2. Okay, so that's taking out, contracting off the C, we get the first, okay, we get minus B wedge C wedge D. Then we get plus, it changes the sign, A wedge C wedge D. A without leaving out B. And we have one term drops out because C dot C is equal to 0. And then we have the final term is minus 2D. Well, no. But anyway, if you look at, okay, we get A plus B plus C, okay? Cross out C, you get A plus B plus D, wedge D, A wedge B wedge. Yeah, I'm dotting out C. So we have A wedge B wedge D. No, A, yeah, C dotted with D is positive. Okay, we get A wedge B wedge C. Okay, anyway, you have to look at it. I think it's all right. So we have, okay, when I dot out the B now, then I get these bivectors. And if you add them all together, you take the dot product here, well, you get a bunch of terms. A dot B, A dot D, minus blah, 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 blah. If you do that, it's not hard because we define they're all negatively correlated. So A dot B is minus 1/2, A dot D is minus 1/2, A dot C is, they're all minus 1/2, except in these terms, A dot A is 0. So you do this, you get A plus B plus C minus 2D, provided I haven't made a mistake. Okay, so now if I square G, I get plus 3. So we define our vector E3, which is orthogonal to E1, F1, and E2 by this expression here. We have shown that G31 is N406, and that's a sub-algebra of the universal algebra, which I denoted by N. So again, I'm introducing geometric algebras in terms of extending the real number systems only by correlated nilpotents or correlated null vectors. I don't say nilpotents because because I want you to think about A, B, and C as being vectors, not bivectors. A bivector can also be a nilpotent if they're, you know, if you have, if commuting bivectors have, well, anti-commuting bivectors, if AB is equal to minus BA, if you square A times B, you get 0. That's simple enough. So, but that's why I say, so we are having Grossman algebra in here as well then, but A plus B plus C minus 2D is a, if you square that out, you'll find that E3 squared is equal to 1. Okay, so now we have the geometric algebra G31. That's the opposite signature of 1, 3. Space-time algebra we used as 1, 3. So now we're looking at the geometric algebra 3-1. You have E1, E2, E3, F1 at this expression. So again, okay, I think you can see there's many possibilities for this. Okay, the last case is 5-1. So in this case, we have oriented our edges all positive and one edge negatively, okay? And then we go through the same calculation. I'm not even going to do that because I think you have the idea now. And so again, we have A wedge, B wedge, C dot this, the same type of calculation. And when we go through it, we find that G squared is equal to 4. We define E2 equal to this. And we have found the geometric algebra G22, okay? Is because we have a basis E1, E2, F1, F2 is equal to R when extended by 4 correlated null vectors, A, B, C, and D. I say completely correlated because that means that A dot B is equal to plus or minus a half. A dot C is equal. That means they're completely correlated, okay? Okay, and now I conclude by saying we have done the calculations for geometric algebra of complete digraphs listed in 3.1 and here. And here we have found the geometric algebras of N4JK equal to 6, 0, 5, 1, and 0, 6. The calculations for the geometric algebras of the complete digraphs correspond to 4, 2, 3, 3, 2, 4, and 1, 5. I haven't done these. I haven't carried out these calculations. However, a few conjectures regarding the geometric algebras of higher order of complete digraphs are made in the next section. Well, all I'm doing here, in general then, if you take for n larger than or equal to 2, you take n, so you can think about n is represented a graph with n things taken 2 at a time, edges. They're all positively, you pick out positive orientation for each edge. And that corresponds to the geometric algebra G1, n minus 1. Well, if you look at the previous cases, you'll see that the cases I worked out fall into that pattern. So I believe, I haven't shown this, but it's conjecture that the digraph, what I call the digraph, complete digraph of n vertices, which we name by null vectors, correlated null vectors, completely correlated null vectors, defines the geometric algebra 1, n minus 1. For n larger than or equal to 2, well, now you can see, again, the edges, it has to add up to the total number of edges, which in this case is 6 edges for n to 4. And I believe that's equal to the geometric algebra G2, n minus 2. And the third conjecture is this. Maybe I've made a mistake, maybe not, I'm not sure, but this is what I believe, but I haven't really worked it out any further. So that's about everything I can tell you right now. But I think it's far more general. I think you can develop calculus. I think it can be applied to quantum computers or quantum mechanics.
Oops.
AT&T
interrupted.
Yes, I think I can. He lost the connection. Okay.
Yeah. Okay.
Okay.
He'll be back. I think he's almost concluding his.
Yes. Okay. He's now here.
Okay, I fell out again.
Yeah.
So okay, I'll share the screen again just so you can see the conjectures.
Okay.
So these fall in the pattern that we've worked out then for all the ones but I'm not I might have made a mistake or something, who knows? But I think it should be very useful in various quantum mechanics and graph theory and many other things. Well, calculus. This type of real. So again, all you have to do to get geometric algebras or Clifford algebras is take the real number system and extend it by correlated null vectors. And it should be widely known. I mean, that's very interesting, I think.
I guess my only question at this point is
I can show you the reference.
some intuition for the meaning of the this digraph. Like so the digraph that you discussed is a way of a kind of extending the signature, I guess.
Well, that's right. We get all geometric algebras this way.
But
because we know that all geometric algebras can be constructed by the way it was been done in terms of matrices before, by coordinate matrices, as I look at it.
So in a sense, well, so your first result then, I guess, would be something like that all Clifford algebras have a representation of this kind, right?
Exactly.
But if you choose a particular, okay, I have a few questions then, I guess. For a given Clifford algebra, is the choice of the digraph unique?
Well, no, it is not unique. In fact, the simplest case that we showed, I'll go back. Let's go back to that slide.
Yeah, so this representation is quite general, just in the same way that representing geometric algebras by matrix algebra, we have different ways of assigning coordinate matrices to the same.
Here, that's right. The geometric algebras are isomorphic to each other, many of them. But here's the simplest case here where it arises. So we associate with the three positively correlated null vectors, the geometric algebra G1, 2, but also with the mixed three digraph, the same geometric algebra as with 0, 3, as with 2, 1, okay? The same geometric algebra. And now with this one, 1, 2, that's the same as 1, 2 up here. So yeah, there's some repetitions there. But each, as I define these digraphs, complete digraphs are associated. It's a one-to-one mapping. It's a one mapping in one direction from these to geometric algebras. But each geometric algebra corresponds to several. Well, for example, 3, 0 corresponds to 1, 2, and 1, 2 corresponds to the same geometric algebra. So how do you call that mapping? It's a mapping, right? But it's not a bijection. It's a many-to-one correspondence, or at least 2-to-1 in this case, 2-to-1 correspondence of the digraphs, complete digraphs, and when I'm calling a digraph, complete digraphs in geometric algebras.
But I think that the question is that you can get many kinds of travel in your graph, and then you are selecting one special travel for this representation of algebra. but are many more travels that are equivalent to this.
Yeah, that's true.
Mhm.
That's true.
And
Well, that's why I'm classifying a particular group, a particular set of graphs of four, well, of n vertices. I'm
yes,
defining where you associate with each edge either a positive 1/2 or negative 1/2.
uh-huh. Mhm.
But you can do it in any way you want. But I say two graphs are the same if when you count the number of positive correlations and negative correlations, you have the same numbers in each case, then they're equivalent graphs. So it's a particular subset of graphs of n vertices that we're talking about. But I think it can be much more general, as you pointed out, we can travel
sorry.
graphs. Pass.
So what what about graphs like a 3-die graph that is something like A plus B minus C plus? Like,
Well, we only pick those sums in minus of when they're equal to plus.
But why not plus minus plus?
Notice interesting, they square, as we looked at, they square to either an integer or I guess it's possible to square to a half or a negative half or a positive or negative multiple of a half or negative 1/2. It looks like it to me.
Oh. But so you're
anyway, but this is again why
I don't. Why these particular 4? Like, why not all 8 combinations? Oops. Uh-oh, we lost.
Maybe.
We lost connection again.
Yes. Mm-hmm.
Oh, here we go again.
Okay. Again here.
You're back?
we'll have to write to AT&T, complain.
So if you just bring back that last share screen. So I'm trying to express my question here. In these examples that you've given, there are only 4 cases that you've considered, but there are really 8 different possible signs.
For a 4 graph, a complete 4 graph, there are 4 edges, 6 edges in all.
No, we're talking about a 3 graph, a 3-die graph.
For 3, there's only 3 edges, right? A triangle.
Yeah, so 3 edges. So it's 2 to the 3 possible sign choices.
Okay, but I'm identifying, yeah, that's certainly true.
So there are 4 more cases here that you haven't considered.
Yeah, let's see, how can I say? But a complete graph of 3 vertices has 3 edges, right?
Correct.
And now if we assign plus 1/2 or minus 1/2 to each of the edges, then there are only,
Then we have 8 possible choices, right?
yeah, but I'm identifying these choices. That's right. Well, let's see, is there something there or not? Yeah, if I take the triangle, I'm going to draw a triangle. I'm sorry, I haven't made figures for this, but we have plus, so each edge can be assigned plus or minus. But again, so I guess I'm taking a combination instead rather than a permutation. The total number, that's right. Yeah, that's right. 2 raised to the 3 power is 8. But if you put all the pluses together, you know, like they're going to be, what are they going to be? You can write them out, but then it's going to be plus, 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 minus, minus, plus, right? And then minus, minus. There's 4 of them.
For example, you can have this travel. I am going to take, like example, the 3rd arrow. Then you can go A, B, C, A. And but you can go A, B, C, minus B, minus A.
Okay.
And then you have one more here.
Well, let's do it in the case of 3, because then, as Bill says, there's 8 possibilities. But I'm saying that what I'm looking at plus, 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 minus, minus, plus, and minus, minus. I'm identifying, so I'm really only taking combination of what 6 things taken 2 at a time, right? Is that what it is?
Okay, but then you are selecting.
Well, 4. That's 4, right?
Okay. Mm-hmm.
So that's what I'm doing. I'm identifying as one graph. The only case I'm considering is plus, 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 minus, minus, plus, minus, minus. So I'm taking the combination of 6 things taken 2 at a time.
Okay, but there are more possibilities of
yes, of course, of course.
Yeah.
But I'm not talking. That's right. I'm identifying a class of graphs. Okay, by where this restriction I'm applying, I'm really taking the combination of 6 edges taken 2 at a time, different cases. In this case, that's important. I should mention that is 4, really. Yeah.
I still don't get it. Like, there seem to be more mixed cases to consider. Like,
Let me see. Let's see. 6 times 5. No, that's not right either, I guess. Divided by 2 is 10, right? Well, that's for, that's for a square. Let's see, let's try and see. The edges is 3 times 2 divided by 2. Yeah, there's something strange there. And let's look at the simplest cases with a triangle. So each edge we assign either a plus sign or a minus sign, plus sign or a minus sign, plus sign or a minus sign. So the final result of that, well, again, is plus. Oh, wait a minute. There's 3 sizes. Okay, you're right. So let's say I have to take plus, plus, minus. Yeah, okay. Yeah, there's something wrong there. So you take a triangle, and so we go plus, 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 and then we have plus, plus, minus. How many cases are there? Maybe there is R8, maybe you're right. well, let's see, then we have plus, minus, minus. So we haven't finished everything then, even the simplest case here. And then we have, well, let's see, minus, minus, minus. Oh, that's all the cases, right? Draw a triangle and label the edges with either a plus or a minus sign, okay? So we can label plus, 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 minus, plus, plus, minus, plus, minus, and minus, minus, minus. 1, 2, 3, 4.
I don't agree. I mean, each edge can be either plus or minus, and you have 3 edges, so that's 8 possible choices.
Yeah, but each triangle will either have how many minuses and pluses? Well, each triangle will either have 3 pluses or, well, it doesn't matter. There's only one with 3 pluses and there's only one with 3 minuses. In the other cases, there will be 2 pluses and a minus, and 2 pluses and a minus, and 2 minuses and a plus. So there's 4 cases then.
So maybe what you're talking about is you don't consider any how should I say, anything other than the
Yeah, that's the same thing as what? That's the same thing as 6 things taken 4 at a time, 2 at a time. Is that what it is? What is that number 4 equal to?
so
6,
these are something like
5,
so you
2
consider a
15.
you're
so-
considering a kind of a ring or something like a loop,
Yeah,
and around the
yeah.
loop you have
yeah, that's right. That's right.
so you don't consider A as a starting point and B as the next one.
No. Yeah, that's right.
So there's no, so they're not labeled in that sense. They're only
Well, of course, with that first and last one, we can plus, 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 and minus, minus, minus. We can think about plus, plus, plus as being clockwise and minus, minus, minus as being counterclockwise. But the other 2 cases are, we can consider plus, plus, minus, and plus, minus, minus. If we start at A in the distinct cases, then that's what I'm associating. Okay, so let's take 3 points, and then the first one we'll go clockwise. The top is A, B, and C going clockwise. Okay, A, B, C. So we can go plus, plus, plus. Okay, that's just going clockwise around the triangle. And we can take plus, plus, minus. Okay, and then we can take plus, minus, minus. Okay, and then we can take minus, minus, minus. So minus, minus. So that's right. The 2 mixed cases are are a little different, or we're identifying those cases with the same geometric algebra. But how can what's the formula for that way of looking at it? How do we get that 4 different cases as a combinatorial type problems?
in the back of my mind. I think I have this name Stirling numbers.
Is that what it is?
It's my first guess.
Okay, I can look that up on. Can look it up on
So
Sterling, right?
how,
Oh.
if you have, say, 2 colors of beads and you have 3 beads and you put them on a necklace, right? How many different possible necklaces can you make?
Oh, okay. Okay.
Yes. But maybe I can understand the viewpoint of Professor Garret, because some of these combinations have not signs in his constructions. Because if he go plus and after he can take minus.
Yeah,
Next, he can take minus.
that's right.
He can only take minus after taking a plus.
That's right. Well, that's right. So we could divide those 8 cases that Dr. Page mentioned into the classes of, like I say, my 4 classes are starting with A at the pyramid top and then going clockwise.
Yes,
B,
you are going
plus, then
block,
plus, minus, minus, and minus, minus, minus.
Okay.
So in that case, let's see. So let's see. So yeah, so that doesn't really make a path, I guess. We have plus, plus, and then the other one is minus. Okay, plus, plus. So that's right. Yeah. So yeah, I guess that we should. That okay. So maybe instead of maybe that's a Stirling. Maybe I should name this thing Stirling graphs or something, because otherwise, if I treated those as vectors starting from at the point taking the origin of the vector A at the top of the pyramid, then plus, plus, minus will just be 3 line segments going downward. So go to A, B, and then minus will take me, won't close the triangle up. And then the other one, plus, minus, minus, will be plus, then minus would be out this way, and then minus again will be, yeah, that's right. So yeah, that's a little, yeah. So that's, yeah, is that a Stirling number? That's interesting. Yeah, I've done
I'm
something,
not
but
absolutely
it's
sure.
what I said I had done. I guess.
It seems less obvious as you increase the number of nodes. Like so.
Well, I can always put the order I just gave you. You know, take the first pluses, put them all together, and then any minuses that are left over. But notice that all the edges in this case add up to 3, right? There's either 3 pluses or 2 pluses and a minus, or 2 minuses and a plus, or 3 minuses. Okay, so with n, the same thing holds true. But again, we're partitioning the graphs up in a different way. Or you can associate then a path, I guess, which is not a closed circle. The only closed paths are plus, 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 and minus, minus, minus. And the other 2 give you a polygon or polygonal shaped figure, plus, plus, minus. So it would be useful, of course, to draw those graphs. But I wonder, that's very important to see whether they're Stirling. Let me look up Stirling numbers and see how that's defined. I have my tablet here. I can look it up quickly.
Sure.
I think that in the case of 3 nodes, there are only 2 different ways of make a complete travel, a closed complete.
Well, that's right. There is no. That's right. It's a double path. And if you go from A to B and then B to A, then you get back.
Yes.
That's with 1 point. Well, that's interesting. You know, I've been thinking about exactly what happens in the case of just 1 point. What do you call that? And one thought, maybe that corresponds to the real or complex numbers. Something like that idea might be interesting. Okay, let's see here. Well, it looks like a Stirling number. Let's see, how does that work? No, I don't see any Stirling numbers that have the value 4. I guess, let's see, is that right? Let's see, is there a table on there?
Well, I think I understand now your argument in the case of 3 graphs, but for 4 graphs, I'm having some difficulty, and so I'm wondering how to extend it. Right?
Well, I can tell you what they are. It's the same idea. Well, let's go down to where I did the.
How did you decide what they are?
Well, here, let's see, where is it? I guess, yeah, maybe that's what it is. Maybe it's 4 thinkings taken 2 at a time. What does that number equal to? 4 times 3 divided by 2 times 1. Okay, that's 6. That's not right. No. Yeah, maybe that. Maybe that's it. That gives the number. So 4 things taken 2 at a time is 6, and that's the same thing as a combination of what? Well, anyway. But certainly we can do the same thing with a square. Okay, start with, say, a square at the top, or at the 12 o'clock position we number A, then at the 3 o'clock we number B, 6 o'clock C, and 9 o'clock D. Okay.
But a square isn't complete though.
Well, no, it's complete. We go A, B, C, and D. So plus.
But there's no AC.
Yeah, that's right. That's right. There's 2 more edges which we can assign anything that we want to. Okay, so that's right. There are a total of okay, that's correct. So yeah, okay, yeah, there is some problems with okay, let's see, how does that work? Well, let's see, we can, but again, we can, I guess, yeah, 1, 2, 3, 4, 5, and 6. Okay, so that's right. Each edge can either be a plus or a minus, So how many different ways then? So I would do it the same way, of course. The sum of all the pluses and minuses will be equal to 1, 2, 3, 4. That's correct number of vertices, right? So J plus K has to equal to N for any of my graphs, right? No. Yeah, equal to 6 in this case. Okay. That's right. So if we start out with 6 edges, that means that all the possibilities are what? 6 things taken 2 at a time, right? And that's equal to 6 times 5 divided by 2 is equal to 15. Okay, so for 4 vertices, there's, well, let's see. Now for pairs, now what am I doing there? I want to take 6 pluses. That's the first case. 1, 2, 3, 4, 5, 6. And now I can change one sign, okay? Then all the rest pluses. Plus, plus, plus. So that's 5, 1 then. So we have 5, 1. And that'll be 7 cases. Well, anyway. Okay, there is something, but you can understand if I take 4 vertices, there will be how many edges? There will be 6 edges. Now each of those edges can be labeled a plus or a minus. Okay, so how many different, if you count up the pluses separately and you count up then any particular graph will have still a total of J plus K equals 6, right? Right? So you have J pluses and you can have K minuses then, okay? And they always add up to 6 then for the class of graphs that I'm talking about with 4 edges. Well, with 4 vertices, okay, and 6 edges. So the number of positive signs and number of negative signs will always be equal to 6 then in that case. Okay, I hope that my conjectures follow that rule too. I certainly need that. Let's see what I conjectured again. Okay, I have to go back here. Yeah, so that's right. So J plus K, 3 conjectures. J plus K must always equal to, of n vertices, must always equal to n things taken 2 at a time. Okay, in this case, we have J pluses and K minuses in any of these graphs. Okay, but I guess that's not really what people mean by digraphs as far as that goes. So that language is not correct. But you understand, I am classifying graphs, okay, by again, where I'm allowing, okay, so with 6 edges, there are how many? There are how many plot? Yeah, so I'm just counting up the number. So it's, yeah, so there'll be 6, what is it? 6 is taken K at a time. Well, it's a decomposition maybe. 6 things taken K at a time plus 6 things taken J at a time must equal to 6 things taken 2 at a time. I guess, is that right? Maybe that's right. Okay, the combination of 6 things taken K at a time plus the combination of 6 things taken J at a time must equal to 6 things taken 2 at a time to be a. Does that make sense or not? I'm not sure.
It's a little too quick for me.
Yeah, maybe it's necessary to review how many paths can you build from an n graph, and then but at the end I have a comment. At the end, I think that it is, we can see your proposal maybe in a different way, like a representation of Clifford algebra and Grassmann algebra in n-graph. I think that it is possible, because in this way, I think that your tables are clear for defining different kinds of paths in the graphs.
Yeah, maybe I haven't counted up counted it up right yet, but I'm sure you can understand what I'm trying to do. I haven't formalized everything in terms of for the problems that you mentioned. Maybe it's not correct that 6 things taken. Well, anyway, we just have to think about that more. But I'm sure it's, there's nothing wrong. I'm just classifying these particular graphs that have all the edges named by J pluses and K minuses being in one class. And okay, so in this case, with triangle, there are what? Well, there's only 4 classes. They're all either plus, plus, plus. There's only one triangle that has one graph that has plus, plus, plus. And for plus, plus, minus, again, we're just assigning pluses and minuses to pairs of vertices, okay? You can either assign a plus or a minus, okay? So that's plus, plus, minus, or plus, minus, 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 minus. Those are the only possible classes. So that's 4 classes then. But counting them up, that's That's right. If you just distribute three things, yeah. Again, it's a combinatorial type thing we're looking at, or permutation, one or the other. Yeah, maybe it's permutations. Well, anyway.
Yeah, well, it's interesting. I from the point of view of physics, my question was sort of leading to, well, how do you interpret this? You suggested, applications in physics, but I didn't quite see how to associate the labeling of the graph, right? The signs in the graph to a particular physical case.
Well, I did show where the space-time algebra arises. That's for example, this case, 2, 2. That's where you have two positive, yeah, I forget now. Yeah, that's 5, 1. Okay, so that's 5. 5 plus 1 is equal to 6, the number of edges there. Okay, well, let's see. What was space-time again? Okay, that was the other one. This one. Oh, yeah, if you take, that's the interesting case. You take 1, 3, you get 6 pluses. They're all positively oriented and correlated, the points. So, yeah, we don't even have to talk about a square, just talk about a simple graph, I guess, right? If you start at a point, you take 3 vectors, arbitrary vectors, you label them by null vectors, and then you just add them together. And you get A, B, C, and D, and then you just add those vectors together. You choose 6 vectors, you assign an orientation to each of them and add them together and accordingly. And that'll give you a graph, right? Maybe not it's only in the case that, let's see if we took the diagonals, take a square, for example, and you take all pluses on the edges going around the square, and then you take the diagonals to be opposite. So you take one diagonal to be plus, and Mira, okay. You look at the orientation of the triangle then. So if you take, well, let's see, how is that? Yeah, plus, and then let's see if we take this one be minus, then let's see. So we have plus, 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 that takes us to here, then minus that. Okay, that means it won't be closed then. That diagonal, it'll be, that's where it'll be a line going down from the edge. The plus, so you can associate a picture with each of those graphs that I'm talking about. In fact, that's what needs to be done. I would need to have good graphs for each of those classes that we're talking about. And that's what's confusing. I haven't done that.
Yeah, I think that would be a worthwhile addition to the paper.
But you agree now, Bill, that Dr. Page, that I can do that. If you put either a plus or a minus on the 3 sides of a triangle, in this case, you get all the possible things that graphs that I'm talking about. But but they are all closed up. Only the first one and the last one close up of those 4, and the others give you a different graph. Now with a square, then if you take the first 4 pluses, that will give you a square. But then you have the diagonal.
You shouldn't be talking about square, I don't think. I think what you mean is a tetrahedron, right? It means a 3-dimensional figure with like a pyramid, right? But with
Well, let's see.
with four sides.
Could you make a figure that has an arbitrary plus and minus sign out of a closed figure? Maybe it's not closed in that. Yeah, oh yeah, that's a good question too. Can you make
So
a?
I'm saying consider a tetrahedron, and now you're
Okay.
going to assign pluses and minuses to each of the edges. Right? And how many different ways are there of assigning, unique ways of assigning plus and minuses?
Well, that
Given
wouldn't be
that
any
you're-
different. Would
Like,
that be any different than a square?
Well, I think so, because there are more ways to change the orientation, right? So that, like, if you think about rotating it, right? You can rotate it. You can rotate a tetrahedron in 3 dimensions.
Well, but I'm not. Yeah, I haven't considered that really. I'm just considering if you take 4 vectors with a square, it'll close, but with a tetrahedron, it won't even close, right? Well, yeah, it would close, but then you're picking different lengths of your vectors too. Plus,
But you said
plus
choose
will close. But
to,
if you added the diagonals, then it would just be a line. If you go plus, minus, plus, and then you take plus again for a yeah, you couldn't make it. Yeah, the diagonals will not be parallel to any of the sides, so it would never close again. Doesn't look like to me. On the other hand, let's see. Yeah, if you took a square, let's see, and you okay, so let's just take plus. Okay, now you take a diagonal. Okay, we can take one anyway. So plus, and now we take the other diagonal to be minus. Well, to the other, so that would take you, that would never close again then. The other diagonal would take you, if you keep, yeah, that would never, well, let's see. I guess you could, but that would take it from the center, for example. No, it doesn't, yeah. Yeah, but it's obviously a very interesting question to which figures, which polyhedra can you draw that makes sense out of this stuff?
Well, you said a complete
But they're
diagram.
not necessarily closed. It can be a polyhedra with an edge sticking out from one end of it or something. But then you talk about rotational symmetries. So maybe it's still the best way to look at it with where all the sides have equal lengths, just to keep things simple as possible. And then, well, you can generalize that too, of course.
In Mathematica, is there a complete package that permit to you to work with graphics and networks? Maybe it could be interesting to see, because all of these properties of graph can be algebraized, and then maybe this can help to understand better the restrictions that is necessary to put in this formulation.
Okay, well, I'd certainly be very grateful if we could all get together and write a joint paper and produce these figures and all this that will clarify all these ideas. Right now I have this paper, which I was planning on putting on my research gate, as a preprint, but certainly there, the ideas can be much further developed, which I expect that's going to be done. But I like could do something altogether, because there's just too many things just to calculate these things. To actually check them requires programming. I only have a old mathematics package. I don't have anything else other than that, and I can't draw figures at all either. So it'd be nice to develop ideas, and I think that it is a pretty simple idea. I think you understand exactly what I'm doing here, and I think it's consistent. But again, I'm not using the language of digraphs correctly either. I noticed that they have formulas for digraphs that in pictures that I've looked at in Google that don't match up with the way I'm looking at it. But I think that I am classifying graphs in the way I talked about. You take any graph with n edges, then you can create, if you assign plus or minus to each of the edges, then you have the number of edges.
Okay, maybe if
Power 2 to the 6th power number. Okay. Well, no, but you can either put plus or minus. So again, we're classifying in this particular way.
Maybe if you can share your.
Yes, I think it would be very useful to have a copy of your paper.
Okay, I'll send you a copy of what I have right now as it stands, and we can take it from there. And certainly, like I say, I'd like to probably put maybe this on. I think that there's something here actually, and I think it needs to be developed. And I can see that I can't do everything by myself, obviously.
Well, let's propose then that you would send us a copy of this, and in 2 weeks' time, we could meet again with specific questions or suggestions, comments. But give us, these 2 weeks to sort of.
Okay, and like I say,
listen.
I'd be very happy if we could combine this into. Well, like I say, I'll probably paste this. Also, put this as a preprint on my research gate, and then
For sure.
Yeah, I'm afraid of. I think the ideas are so simple. I'm not sure how much is. Like I say, I believe now that when there was a talk about graph theory at this other conference, the virtual conference I went to, but using Grossman algebras. It was a very nice talk, actually. And you can say that I should probably reference that in this paper here. I think everything is really wide open. There's many possibilities, I think.
Okay. Well, thank you very much for this new material and the sort of the extension to this idea of duality. That I think is like a valuable sort of research area that will help us maybe even to appreciate what duality means in general.
Well, that's the thing. I believe that duality that's what stopped other people from doing it in this way, because duality is taking a vector space. The dual space is, of course, into scalars, but somehow that stops people from thinking in the terms that I'm thinking here, where these inner products either plus or half or minus a half. Anyway.
Okay. Well, thank you very much for the presentation and discussion today, and we can agree, I think, to meet again in 2 weeks' time. If everyone is available.
That's fine. And we won't. I'll keep working too, and also I hope we can get some decent figures. Maybe if either of you could produce figures, that would be great. And well, anything, we can all divide the time up and just speak, not say any one person is going to speak all the time.
Okay. Okay, maybe we can take a time for presenting our questions and ideas about.
No, that's right. Maybe, like I say, maybe it'll lead to a joint three-man paper. That would be well, we can see what happens. Maybe it's already all known. I don't know.
Okay. Well, let's meet again in 2 weeks, and we'll go from there.
Okay, that's fine. I appreciate. It's been very enjoyable getting these other perspectives that you brought to this.
Okay, and in the meantime, I'll review my knowledge of Stirling numbers in case that might be useful.
Yeah, maybe a little bit of graph theory too.
Yes, of course.
I need to do it.
Well,
I don't know anything about graph
well,
theory.
see you in 2 weeks then.
Oh, that's
Okay.
perfect. I'm
Bye.
Bye.
Okay, take care, both of you. Adios.
Bye.
Adios.